Good morning. This is our second lecture in Chapter 5 dealing with the metal oxide semiconductor field effect transistor. Last time we talked about the case where VDS was very small, less than 50 millivolts. Today we're going to move into a more robust description of the triode region of operation and then also talking about the saturation region of operation. We're also going to talk about the difference between enhancement and depletion modes for transistors. So this is actually a lecture that's going to cover a lot. Probably the most important material in this chapter. And then next week, we will dive into more examples and a more detailed description of how the MOSFET can be used to design amplifiers. Good morning, everyone. We are in Chapter 5. We're talking about MOSFETs. And we're going to pick up where we left off last time. I'm happy to say that I was able to fix the problem with the equations displaying in an unusual way. So that won't be an issue today. So where are we? We're talking about the MOSFET when VDS, the voltage applied across the drain and the source, is either zero, meaning they're both grounded, or very small, less than 50 millivolts. And what we saw was, for those cases, or that case, the linear region, we can define the VI relationship by this resistance RDS, meaning that it's linear, a constant ratio between the two. And that value of RDS is dependent on several different values: the process transconductance parameter, the aspect ratio, as well as the overdrive voltage. Now, and then we showed this graph which simply demonstrates that down here we have one case with high resistance, low overdrive voltage. Up here we have low resistance, high overdrive voltage. And so essentially it's that overdrive voltage, which is VGS, that allows us to control the resistance. Okay, so this is what we're moving on to next, which is operation as VDS goes up. So what happens to the current ID when VDS is increased beyond the small value, meaning greater than 50 millivolts? What happens is the relationship between them ceases to be linear, which means we're no longer going to be able to describe it by this nice RDS value. Now we could define an RDS, but it would be a nonlinear value, a function of VDS itself. It would no longer be a single value. So how can this nonlinearity be explained? What we're going to do for the time being is we're going to assume that VGS is held constant, because it's going to make it more difficult to try to look at the variation or the effect of variation in two variables as opposed to one. So let's just focus on one variable. And we're going to assume that the VDS applied is applied and appears as a voltage across the N channel. This is not really an assumption. This is the reality. This is the way it works. And so note that the voltage decrease from VGS at the source end of the channel to VGD at the drain end. Anyway, these equations are best explained by the picture on the next slide, which I think is where we left off last time. So what we see here is we have our drain, we have our source, we have our gate, okay? And the difference over here, this voltage difference, is VGS, okay? Because S is grounded. The difference over here is going to be VGS minus VDS, because S is the ground, right here. And so what that ends up giving us is, as you can see on this previous slide right here, it ends up giving us VGD. So we're going to call this difference right here VGD. Now, VGD is going to be less than VGS. This difference here is big or bigger, and this difference over here is small or smaller. And so what ends up happening is that that will be proportional to the depth of the channel on either side. You'll see that the depth on the left-hand side is greater than the depth on the right-hand side. And so what was once a rectangle now begins to sort of look like a trapezoid, where this end is pushed up in a manner proportional to whatever VDS is. When VDS was equal to 0, we had a rectangle. As VDS increases, it'll continue to push that end up. And so this is what we are going to see when we are looking at the triode region of operation, which is where we are now. Now, note that the triode region of operation also included the case we were looking at with the less than 50 millivolts. So that still falls inside of the triode region, but that was a special case. We called that the linear triode region. So now we're just looking at the regular old triode region. Okay, so note that we can define the total charge stored in the channel as the area of the trapezoid. And what that means is that the amount of charge stored in the channel is proportional to its area. More area, and again, really we should be talking about volume, but we're looking at this in a two-dimensional manner and assuming that the third dimension is static, right? So if you think about it like this, we're assuming that the other dimension doesn't have any, right? This depth is the same. It doesn't change from one side to the other. So we can just, so in that case, right, the charge is proportional to the cross-sectional area because the depth is constant on either side. Okay, so now, what we see is that the amount of charge stored is proportional to the overdrive voltage minus 1/2 VDS times L. Now, where do we get that from? That is actually, you can see, comes from the way that we calculate the area of a trapezoid, okay? Right, because if we were to calculate the area of the whole rectangle, what would that be equal to? That would be equal to our VOV times L, right? But for the trapezoid, we have to take out this triangle down here. And so what we're going to do is subtract out the area of the triangle, which is 1/2 base times width, which is 1/2. The base is L, and the width is VDS. Okay, and so what that leads us to is essentially the same equation shown right here, which is VOV minus 1/2 VDS times L. So that's how we come up with that equation. It's all based on the area stored right inside of here. Okay, right, so I think we've already explained this nonlinearity. Okay, this is done. And now what we end up with is a set of equations. So when we're analyzing a MOSFET, whenever we have a problem, we're going to have to first figure out which region of operation it is that we're in. And so we've learned about a couple of them so far, right? There's the case where VDS equals 0. There's the case where VDS is less than 50 millivolts. And then there's going to be the case where we're in the triode region, where again, really all three of these fall within the triode region. The fourth one is called the saturation region of operation, and there will actually be a fifth as well. But the point I want to make here is that it's important to figure out which region of operation you're in, because that will tell you which equation it is that you need to use. So for example, in 514 down here, this equation is for the triode operation. This down here, we haven't explained this one yet, but this is for what we call the saturation region of operation. So let's talk more about saturation. What is saturation? Where do we shift over to saturation? It's all based on this right here. This line determines the boundary between triode and saturation, and the breakpoint is when VDS is equal to VOV. So when VDS is less than VOV, we're in triode. When VDS is greater than VOV, we have saturation. And this picture right here illustrates that relationship. The triode region has this curvature to it. What we see is in the triode region of operation, the value of ID is equal or is dependent on both VDS and VOV. Once we enter the saturation region, it flattens out, and so ID will be dependent on VOV only, right? The effect of VDS is not there. It's a flat line. Now our linear region would be right in here, and you can see in this region it looks somewhat like a line. So this is the linear subregion within the triode. And again, we have two equations that we need to deal with: triode and saturation. All right. So in section 515, we assume that the N channel is tapered, but channel pinch off does not occur. And what that means is that we had originally a rectangle, which became a trapezoid and can become a smaller trapezoid, but it would only move as far up as to become a triangle. And this actually represents the boundary between the triode and the saturation. When the rectangle goes from a trapezoid and then shrinks down to a triangle, that's the boundary that we're talking about right here. What is pinch off? Pinch off is when what could potentially happen is that because the voltage over here continues to increase, this point actually begins to pull back and move to the left. So, we are not going to consider pinch off yet. We're just going to assume that doesn't happen. So the rectangle becomes a trapezoid, becomes a triangle, and it stops there. And this is what happens when VDS is greater than VOV. MOSFET enters the saturation region. Any further increase in VDS has no effect on ID and no effect on the shape of the inversion layer. Okay, which is right here. So let's take a look at an example. This is example 5.1 from the textbook. And it is an NMOS type MOSFET. So consider an NMOS process technology for which the value L min is equal to 0.4 micrometers. The distance between the plates is 8 nanometers. The electron mobility is 450 centimeters squared per volt second, and the threshold voltage is VT. Okay, so first it asks us to find the oxide capacitance and the, remember this is the process transconductance parameter because it has that that prime little dash thingy here. Okay, and then we'll move on to the other parts. All right, so this is pretty straightforward. It's COX is equal to the permittivity divided by the distance between the plates, or the thickness. That was the word I was looking for. We plug in the two values that we know, and that gives us a value of 4.32 femtofarads per micrometer squared. Okay, next, we want to calculate the value of the process transconductance parameter, which is the mobility times the oxide capacitance. This was given to us. This we just calculated from above. And so we are left with 194 microamps per volt squared. Now, you have to be careful when you're doing this right here, because the units, right, they need to be accounted for. And so let's show quickly how we would account for just the unit. So forget about the number. I'm just going to say alpha, and then let's say centimeters squared. So what is that going to be actually? That is going to be 10 to the negative 2 squared meters per centimeter. Okay, and we're going to multiply that by, they're both squared, okay, and so actually all of them are squared, and so that will be multiplied by our centimeters squared per volt second, and so that will cancel out, and that will appropriately scale our alpha. For the other one, we'll have beta, and that'll be 10 to the negative 12 farads per femtofarad, and we'll multiply that. Actually, that should be upside down. I can't erase here, unfortunately, so I'll say this to the negative 1 femtofarads per micrometer. Well, I ran out of room. Anyway, hopefully you get what I was trying to show here, is that you have to take into account for the units. So I recommend that you try this calculation right here to make sure that you end up with the same value and you can account for the units properly. If you have questions about this, feel free to ask during the synchronous lecture, during the live lecture, and I'll chime in on that. Okay. The next step, well, actually now we moved on to the next part of the problem, where it says for a MOSFET with an aspect ratio of 8 micrometers over 0.8 micrometers, calculate the values of VOV, VGS, and VDS minimum required to operate the transistor in the saturation region with a DC current of 100 microamps. So, what is it asking us? It says VDS minimum. How do we know what the minimum is? Remember, when I draw, if I could draw this graph right here, where this is VDS and this is ID, and this is the boundary between saturation and triode, the minimum VDS value is going to be the boundary, which is equal to VOV. So what we're going to be looking for, as you can see down here, is the case where VDS is equal to VOV. So this equation here is the equation for the saturation region of operation. We had shown this before. We are going to set it equal to 100 microamps because that value is given to us up here. We know what the device transconductance parameter is. We know what the aspect ratio is. And now all we have to do is just flip this around and solve for VOV squared, which is what we do moving down to the bottom. So we end up with a value of VOV, which is 0.32 volts. And because we're operating at this point right here, we also know that VDS is equal to VOV is equal to 0.32 volts. So this is an important part of this chapter, like any chapter, is being able to decipher what the problem is asking us, and that is always a challenge. Okay, the next part of the problem says, for the device in part B, find the values of overdrive voltage and gate source voltage required to cause the device to operate as a 1000 ohm resistor for a very small VGS. So again, here, if I were to draw where we are on this graph, we are going to be down here in the linear region. This is a good little exercise to do whenever you're dealing with problems in this chapter is to kind of imagine where you are on the VI curve. Because once you can figure that out, then it's just a matter of pulling the right equation and using some algebra. All right, so we have our expression for RDS, which is, again, dependent on the process transconductance parameters, dependent on the aspect ratio. And so we want to go back and figure out what the value of VOV is. This is what we don't know. So anyway, like usual, we invert. We use algebra to solve. Hopefully you can take a look at that on your own. Here you can see I've also been very careful to outline what's going on with the units. And in the end, we get 0.52 volts. So this is one of the answers. Then it asks us to find VGS. And we know that VOV is equal to VGS minus the threshold voltage. We know VOV, we know the threshold voltage. We add them together, and that gives us a VGS of 1.22 volts. Okay. So that was a good example showing us how to work with the NMOS transistor. What about the PMOS? So as you can imagine, there is an quote-unquote opposite way to set this up, where we have an N-type substrate and we have two wells that are P-type substrates. Essentially, it will work exactly the same way as the NMOS, with the exception of all the fields, the electric field polarity being reversed, and we are going to form a P channel instead of an N channel. Before, right, we had the positive particles that were pushed away and the negative particles that were drawn in. That's not what will happen here. We'll have negative particles that will be pushed away, and we'll have positive particles that will be pulled in. As you can imagine, you have to set a negative voltage here in order to generate the appropriate magnetic electric field. But other than that, it works exactly the same way. So complementary devices, this is a term we use to refer to the P and the N channel MOSFETs. They're complementary to one another. And if you've ever heard the word CMOS technology, complementary MOSFET technology, that's one where both P and N type devices are being used at the same time, or on the same wafer. So what are the main differences between the N and the P channel type devices? Right, we need to apply a negative, not a positive voltage to the gate in order to close the channel and create a path for current to flow. The threshold voltage, previously represented as VT, we'll call that VTP. And in order to close the channel, the absolute magnitude of VGS needs to be greater than the absolute magnitude of VTP. That comes from the fact that the voltages are negative. You could use that same expression for the NMOS, but because both the voltages are positive, it doesn't really matter. So other main differences, the process transconductance parameters are defined differently. Obviously, we need to use hole mobility as opposed to electron mobility, but other than that, right, it's pretty much the same. And then the rest is analogous, but with the polarity is reversed. For the purposes of being, well, I don't know what the right word is, for the purposes of making it easier to do homework and easier to study for exams, what I'm going to do is, you will have homework problems that are on the PMOS, but your exam problems will focus on the NMOS as far as mathematical problems. And I'll talk more about that when we do the live lecture. But anyway, for the most part, we're going to be more focusing on NMOS to illustrate the fundamentals, the basics of the operation, and then extending that to the PMOS. Now, PMOS technology originally dominated the MOS field over NMOS. However, as manufacturing difficulties associated with the NMOS were solved, They, meaning the NMOS, took over. Why is NMOS advantageous over PMOS? Because electron mobility is 2 to 4 times greater than hole mobility, and this is something that we've seen before. And so, again, you get more bang for your buck using NMOS, meaning a greater range of conductivities, than you would with the PMOS. I talked about this a second ago, the CMOS technology, and that is a technology which allows fabrication of both N and PMOS transistors on a single chip. So this is a cross-sectional area of a CMOS wafer. And so what you can see is if you use a P-type body, then the NMOS is constructed in pretty much what I would say the normal manner. The PMOS, however, right, you can't make that directly in the P-type body. So you have to add an additional well of N-type, and then you have your wells of P-type within that. You also need to have very thick a dielectric material to isolate the transistors from one another. So you can see there are some more difficulties that are associated with making this kind of hardware as compared to just doing regular old PMOS or regular old NMOS. So more difficult to fabricate, but it is more flexible and powerful because hopefully in this class we will get to some applications that require both PMOS and NMOS for the same design. And so having access to both types of devices can make certain types of designs way more efficient as opposed to having to rely on one only. And now this is more prevalent than either NMOS or PMOS. So the vast majority of devices are based on CMOS technology. I think we've already talked about this primarily, right? We have the P-type semiconductor, which provides the base for the NMOS. We have the dielectric to separate and isolate the transistors from one another. And we have the N-well, which is needed to house the PMOS. Okay, so quick recap here. What have we learned so far? We have learned how the MOSFET works when VDS is much, much less than VOV, and this is the linear region that we talked about. We've also talked about this here, right? When VDS is less than VOV. So we call this the linear region. We call this the triode region, although again, remember the linear really is part of the triode. And then we have the case for when VDS is greater than VOV. This is the saturation region. And there's one more that we have not covered yet. And this is going to be the region that takes into account something called channel length modulation. So that is going to come into play when VDS is much, much greater than VOV. And we have moved further over into this region to the right. This is homework 11, so I'll be assigning that today. This lecture, I guess technically, is the lecture for Friday, April 10th. So if you're trying to keep up the regular schedule in terms of doing homeworks, that would mean that this would be due on, for your own purposes, should be due on, let me look up, I guess it would be the 17th. Right, obviously, this only applies to the 2020 version of this course. If you're looking at this in a future year, then that date would be different. Here's the solution. Okay, so now current voltage characteristics. Right, figure 511 shows an N-channel enhancement MOSFET. There are 4 terminals: the drain, the gate, the body, and the source, although normally it's assumed that the body and the source are connected. So just a quick little overview of different symbols that you may see here. Although a MOSFET is symmetrical, we often will designate the terminals as source and drain based on the polarity of the voltage being applied. So the drain is always assumed to be where the positive terminal is applied, and source is either grounded or would be where the negative terminal is applied. And so these arrowheads here, they designate the normal direction of current flow. But like, as you can see, this is all dependent on your definition of how it works. Normally, you would choose to follow the convention. Okay, so table 5.1 provides a nice overview here of the NMOS, but I want to talk about enhancement and depletion type MOSFETs. We've used those terms, but the slide that used to outline the difference, for some reason, is not in here anymore. So I decided to just write it in real quick. So far, we've been talking about enhancement type MOSFETs. They are more common where the device is off when VGS is equal to 0. This means that if you have an NMOS type device, you increase the value from 0 upward in order to turn it on. With a PMOS, you decrease the value downward from 0 in order to turn it on. Same thing. Now, a depletion type transistor is less common, and it's a device which is on when VGS is equal to 0. So this is off when VGS is equal to 0. This is on when VGS is equal to 0. And so you have the corresponding changes to how you would manipulate the PMOS and NMOS operation. Like how I spoke about NMOS, same thing with depletion and enhancement type or depletion and enhancement modes. So we're going to focus mostly on enhancement type NMOS transistors. You should be aware of how depletion type works. You, I think, do have one homework problem which talks about a depletion type transistor. But just for the sake of simplicity and not throwing too many different variations, similar variations of the same thing at you, I'm going to focus on the enhancement type. Now, so what does this table 5.1 have? This is a table that you're going to see in your cheat sheet. It has a lot. So you can see it has a general circuit diagram for the NMOS showing all the connections. You can see here we have, you can see here we have the VI characteristic. It shows the saturation and the triode regions of operation. It shows, different equations here. It's a little bit small, but, what is the inequality for triode? What is the inequality for saturation? What is the current value for the saturation? Anyway, lots of stuff. And then also down here, you can see a little bit of a summary of both the triode and saturation region, or how the device operates in the triode and the saturation regions of operation. So it's a really good summary. And I would say, if you can understand this table 5.1 well, then that's a good thing. That really shows, I think, that you have a more solid understanding of how this device works. And plus, it's a really great reference to find everything all in one spot. So like I said, at the top of the table, it shows the circuit consisting of the two sources, etc. Right. I mean, I think that a lot of this right here, we've already said. Here's a larger version of the table. When we present this using the projector, this is important. It's easier for the students to see. Okay. So now let's take a look at a little bit more detailed VI characteristic for the NMOS. All right. So first things first. You can see there's the split between the triode and the saturation regions. This is where VOV is equal to VDS. But you'll note that there are also going to be different lines here because there are going to be different VI curves depending on your value of VGS. So as VGS goes up, as the overdrive voltage goes up, the saturation value of ID also goes up. So we could call this ID4, we could call this ID3, ID2, etc. So as you increase VGS, you also increase the saturation current. Now, the other thing you'll note is that the boundary between the saturation and the triode regions also moves. So as we get larger and larger, a larger and larger value of VGS, that point moves further to the right. And this makes sense because, right, it represents the equality between those two. So what's the main takeaway here from this graph? It's really just demonstrating how the behavior of the MOSFET compares between one value of overdrive voltage or value of VGS and then either increasing or decreasing that. So this is a graph that I think is one that you need to take a look at on your own and sort of draw your own conclusions. Okay, so when MOSFETs are employed to design an amplifier, and this is essentially what we're working toward at the end here, is using a MOSFET to design an amplifier, in what range will they be operated? And the answer to that is the saturation region. So, in the saturation region, the drain current is dependent on VGS because you can see it does change. ID changes as you go up from one line to the next, and that's changes in VGS. But it's independent of VDS, and that's reflected by the fact that the slope is flat, right? It is not proportional to our VDS. Now, in effect, what this means is that in this region here, okay, you have a voltage-controlled current source, and this is one of the keys for amplification. What does a voltage-controlled current source look like? Right, we've seen this before, especially in Chapter 1, and then more so in the circuits class. Darn it. One equation I did not fix. Okay, sorry about that. So, in effect, the MOSFET becomes a voltage-controlled current source when we're in saturation region. This is key for amplification, and you can see this in 521 as shown here. So what's one problem with this equation 521? Essentially, it's nonlinear with respect to VOV. So what that means is that you are not going to have a constant gain, right? Your goal is to have V out is equal to some constant times V in. You don't want to have a constant that's a function of V in times V in because then, right, you have a nonlinear relationship, and that's not the way that's not an ideal characteristic for an amplifier. So what that means is that we have to find a way to linearize this this device. All right, so this is a view of the transistor as a voltage-controlled current source. And so this, I think, is a good spot to end. Next time, we will talk more about this version or this representation of the MOSFET. We'll also talk more about how this leads us into designing an amplifier, and we'll have more examples that we are going to take a look at.